What if I told you that a huge part of physics, some of the most fundamental ideas about energy and the universe, all hinge on one simple, almost philosophical choice you have to make? I'm serious. What if the key to solving some massive problem about heat, work, and energy all came down to where you decide to draw a line? It sounds kind of crazy, right? But it's the absolute secret to understanding thermodynamics. You see, before we can even begin to talk about energy, we have to do something really basic. We have to decide what part of the universe we actually care about. In physics, we call that little piece of the universe our system. It could be anything: a car engine, a single living cell, a star, you name it. And here's the cool part. Once you've picked your system, everything else, and I mean literally everything else in the entire universe, we just lump it all together and call it the surroundings. It's our thing versus everything else. And that line we draw between them? Oh, that's where all the action is.
Now, this line isn't just some passive, imaginary divider. We call it the boundary. You should think of it like a bouncer at a club. It's an active gatekeeper with a very specific set of rules, and it decides what gets in and what gets out. And really, it's only looking for two things on the guest list: matter and energy.
Okay, let's look at rule number 1, matter. Can actual stuff, atoms and molecules, get in or out? If the boundary says, sure, come on through, like steam escaping a boiling pot, we call it permeable. If the boundary is like a locked door keeping everything inside, think a sealed can of soup, then it's impermeable. Simple enough.
Next up is energy, and one way it moves is as heat. If your boundary lets heat pass right through it, like a metal pan on a stove, we've got a fancy word for that: diathermal. But if it's really good at blocking heat, like the insulated walls of a great thermos, we call that adiabatic. It's basically a heat shield.
And energy can also cross the boundary as work. This is all about one simple question: can the boundary move? If its walls can expand or contract, like the piston in an engine, we call that boundary movable. That allows the system to do work. But if the walls are stuck in place, totally unmoving, we call it rigid. The volume is locked in. So based on those simple rules, matter, heat, work, we can now classify literally any system in the universe. It turns out they all fall into one of 3 main categories. 3 kingdoms, if you will. And trust me, this classification is the key to everything. First up, we've got the true hermit of the universe, the isolated system. I mean, this thing is completely sealed off from everything. Its boundary is impermeable, so no matter gets in or out. It's adiabatic, so no heat can cross. And it's rigid, so no work can be done. It's basically in solitary confinement. And this total lockdown has a huge, huge consequence. Because nothing, no matter, no energy can get in or out. The total energy inside that system, what we call its internal energy, or U, it's stuck. It can never, ever change. The change in U is always 0, period. Okay, system number 2. This is the real workhorse of thermodynamics, the one we deal with all the time. The closed system. The rule here is that the boundary is impermeable. The matter is trapped inside. But, and this is the key part, energy is free to come and go. Remember that can of soup? The soup isn't going anywhere, but you'd better believe the heat from the stove is getting in. And the behavior of these closed systems is perfectly described by one of the absolute pillars of physics, a law so fundamental you've definitely heard of it. Yep, the first law of thermodynamics. And honestly, it's just accounting for energy. It's a balance sheet. All it says is that any change in the system's internal energy, delta U, has to come from somewhere. It must be equal to the heat you add to the system, that's Q, plus any work that's done on the system, that's W. That's it. It's just conservation of energy. No energy is created or destroyed. You just have to track where it all goes. And that brings us to the third and final kingdom, which is maybe the most exciting of all, the open system. Here, the doors are wide open. The boundary is permeable, so both matter and energy are flowing in and out. A jet engine, a river, or, well, you. You are a walking, talking, open system. And this is why open systems are just so incredibly cool. They can exist in what we call a non-equilibrium steady state. Now, that sounds like a mouthful, but it's actually how life works. Think about it. A living cell is a whirlwind of activity. Food comes in, waste goes out, energy is constantly being processed. But through all that chaos, it maintains a stable, organized structure. That amazing balancing act is only possible because it's open. In a very real sense, that constant flow is the state of being alive.
All right, so the ideas seem pretty clear, right? But there are a couple of classic mistakes people make, so let's do a quick reality check and get those sorted out right now.
Misconception number 1. People hear closed system and think nothing gets in or out. Wrong. A closed system is only closed to matter. The energy door can still be wide open. Our can of soup is a closed system, but you can definitely heat it up. It's absolutely exchanging energy with the stove.
And number 2, the idea that you can find a perfectly isolated system just lying around. In reality, not so much. It's a theoretical ideal, a useful concept, but you can't actually build a box that stops every single bit of heat from leaking out forever. The only thing we consider to be a truly perfectly isolated system is, well, the entire universe.
Okay, we've defined the systems, we've busted the myths. Now we get to the big idea, the deep insight. This is why that imaginary line we talked about at the beginning is everything. Here it is. The system you choose to define literally changes the physics of the problem. No, I'm not exaggerating. It's not just some label you slap on. It changes the rules. It changes the equations you use. It changes your entire analysis. Let me show you what I mean with a great example.
So this device is a bomb calorimeter used to measure the energy in food. Now watch. Choice number 1. Let's draw our imaginary line only around the burning peanut inside. Okay, matter is trapped, but energy is pouring out as heat. That's a closed system. We'd use the first law to analyze it. But what if we just redraw the line? Now let's draw the boundary around the entire insulated device. Suddenly, it's an isolated system. Nothing gets out of the whole box. The total energy inside is now constant.
Think about that. Nothing physically changed. The peanut is still in the box. All we did was change where we drew an imaginary line in our heads. And just by doing that, we completely changed the rules of the game. We flipped the problem from a closed system where we track energy flow to an isolated system where energy is simply conserved. And that is the ultimate takeaway here. When you are staring down any problem in thermodynamics, the most important, most critical first step, it isn't grabbing a calculator and it's not looking up a formula. It's deciding what your system is. Because that single choice, that simple act of drawing a line, determines everything that comes after. It's the key that unlocks the entire problem.